Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 5th, 2026, exactly 1 week ago. It presents a novel approach called SHARE that achieves up to a 100 times reduction in trainable parameters and roughly 280 times memory savings compared to standard low-rank adaptation techniques. The paper is titled, Shared LoRA Subspaces for Almost Strict Continual Learning, and as we'll see later, the results for efficient, lifelong learning are really impressive. To illustrate the core hypothesis, Figure 1 presents evidence for what the authors call a shared foundational subspace. The chart plots the similarity of model weights, measured by a metric called centered kernel alignment, against the number of sequential tasks performed. You see 3 colored lines, which represent models initialized with different task subsets. Notice how all 3 trajectories slope upward and converge into the orange shaded region at the top. This implies that regardless of the starting point, the adapters naturally align toward a universal structure that works across diverse tasks. So, having seen that tasks naturally converge, Figure 2 details the share mechanism that leverages this effectively. The pipeline splits into 3 stages. First, initialization on the left extracts principal factors, labeled alpha 0 and beta 0, from existing adapters to form a frozen shared basis, indicated by the snowflakes. Then, in the middle continual adaptation phase, the model handles new data by training only small, temporary factors and coefficients, marked with flame icons. Finally, the merging and fine-tuning step on the right mathematically integrates these updates back into the shared subspace, allowing the foundation to evolve without catastrophic forgetting. Alright, following that explanation of the mechanism, Table 1 presents the results on the continual glue benchmark. The most striking detail is the efficiency gap in the second and third columns. While standard LoRA requires 80 megabytes of memory for 6 tasks, SHARE shrinks this to less than half a megabyte. In the middle section, notice the green arrows. These indicate backward transfer, where learning a new task actually boosts performance on an earlier one. Finally, the bottom row shows that SHARE Full maintains an average score of 83.44%, effectively matching the baseline. Moving from text to visuals, Figure 3 illustrates the method's performance on text to image generation tasks. The top row presents results from standard low-rank adaptation models, where a separate adapter was trained from scratch for each specific style, such as SpongeBob or Soviet propaganda. In contrast, the bottom row shows images from a single SHARE model that learned these 4 styles sequentially. The generated samples are nearly indistinguishable between the 2 rows, which confirms that SHARE successfully integrates diverse visual concepts without the catastrophic forgetting that usually plagues continual learning. While the previous figure focused on generation, Table 2 now quantifies performance on standard image classification benchmarks like CIFAR 100 and Food 100. The second column highlights the efficiency advantage. SHARE operates with just 0.1 million parameters, significantly fewer than prompt-based methods like dual prompt. Moving to the results, the CIFAR 100 column shows that SHARE hits 94.2% accuracy, effectively matching the theoretical upper bound. Moreover, the low forgetting rates across all datasets demonstrate that the shared subspace prevents the model from overwriting earlier skills. Alright, moving from 2D images to 3D geometry, Table 3 evaluates continual pose estimation on the Pascal 3D Plus dataset. The standout result appears in the parameters column, where data replay methods like INEMO need 25 million parameters to retain knowledge, while SHARE operates with just 1 million. Despite this massive reduction, the accuracy scores across the Pascal 3D and occlusion columns, L1 through L3, show that SHARE consistently beats those heavier baselines. It effectively rivals the theoretical upper bound, proving it preserves complex spatial reasoning without needing to replay old training examples. So, having demonstrated capabilities in specific domains like 3D pose, Table 5 provides a granular look at stability over a longer sequence of 11 tasks. This matrix tracks performance using Rouge L scores, where rows represent the model's state after learning a new task, and columns correspond to specific past tasks. The orange diagonal marks the baseline performance of 1.0 when a task is first introduced. Scanning down the first column for task 1 shows the retention. Even after 10 subsequent tasks, the score only dips to 0.91. Looking at the bottom row, which shows the final model state, we see consistently high scores across all tasks, confirming that SHARE effectively locks in knowledge without significant decay. Wrapping up, 2 takeaways stand out. First, SHARE demonstrates that a single evolving subspace can replace hundreds of task-specific adapters, slashing memory usage by nearly 300 times. Second, It achieves this without data replay, enabling large models to continuously adapt in the real world without the massive cost of retraining. This offers a practical path towards scalable, lifelong learning systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.